So far, you guys have looked at objects moving at constant velocity. The position time graph looked like this. As time passed, the position changed in a linear fashion, which meant as each instant went by, you went the same distance. It's time to move on to more interesting motion. We haven't talked at all about what causes constant velocity or what we could do to change an object's velocity, and that's what I'd like to go into next. To start this discussion, I'd like you to look at one more constant velocity motion, a car coasting down a table. What I've got here is a motion detector. And a motion detector, it actually works the same way a bat, the little furry flying mammal, goes hunting. A bat uses something called echolocation, which means it sends out a click of sound. That sound goes off, it bounces off its target, it bounces back. And the bat's brain can actually process the difference in time between when it clicked and when it heard its click. And that lets it make a map of where bugs are and things like that. So this thing does something similar. There's a sensor here that makes a click, and it sends the clicks out, and it's going to reflect off this stack of textbooks I got here. And those clicks are going to bounce back and be detected by the computer. So I'm just going to go over here to start. Give it a push. And now stop. So we have this graph here. Since this is a position time graph, we can see that there's horizontal, slope of 0. That's when the cart was not moving. We then have a positive slope that's relatively constant. It was going in this direction. And then, after I stopped it, back to a slope of 0. That's when it was stopped down there. The reason I wanted you to see that particular motion was, unlike our other constant velocity motions, there was nothing keeping that cart going. In the other labs, we had someone walking and their muscles were pushing, or there was a motorized vehicle, but here it just coasted. And you saw from the graph that was plotted on the screen, it appeared to be constant velocity. It appeared to be a straight line. Now we know that that wouldn't have gone on forever. We know it would have slowed down. But a guy named Galileo Galilei in the 1500s, he realized that the only reason it would slow down was because there was something messing with that cart. There was something pushing on it. And pushes or pulls are the next topic we're going to have to discover if we want to understand how motion changes. Galileo began to formulate what we now call Newton's first law. And we will go into Newton's first laws a lot more detail in a couple weeks. But most of you can probably repeat them from heart. They get beaten into your head in middle school. So Newton's first law: objects in motion stay in motion unless acted on by a force. Objects at rest stay at rest unless acted on by a force. There's a certain parallelness to those two statements. So you could kind of combine these two and say objects keep doing what they're doing unless you force them to do otherwise. So you want to change an object's motion, you need a force. And that becomes the heart of Newton's second law. This isn't all of Newton's second law. It's actually a very important mathematical law that we'll learn eventually. But you want to have an acceleration, you want something to not always travel the same distance in the same amount of time, you need a force to do it. So before we talk at all about accelerations and changing motion, we got to at least mention forces. So what's a force? It's a push or a pull. So I thought it would be good if we went through and looked at some common pushes or pulls. So the one that we will study first, and the one you're most familiar with, is gravity. I pushed that cart down the table. It mostly continued at constant speed. That would not be the case if I had thrown it up in the air, like I'm going to do with this angry bird. It goes up, it slows down, it stops, it comes back down. You know gravity was pulling it down. But that caused a change in motion. We had our initial velocity lost and decreased, and then a new velocity in the opposite direction was gained. So the force of gravity is going to be one of the first forces that we want to study. This spring scale. There's literally a spring, and the more you pull on it, the more it pulls back on you. So it's actually not measuring the weight, it's measuring how much this spring is stretched. So what does that have to do with weight? Well, here's my spring scale, and clearly we're interested in how much the Earth is pulling on that kilogram. So we're interested in the force of gravity. But that kilogram, it's not falling down. And if this was the only force on it, it would be. So there must be some other force acting. And that force is an upward force. And the reason the kilogram's not moving is because these forces are balanced. We could call this a spring force, but it's actually also a tension force. What's literally happening is in that spring, in this scale, atoms are being pulled apart, but they have such strong chemical bonds because of their electrons that they're resisting it. And it's deforming the spring and stretching the spring out, but the spring can take it. And the two forces are balanced, and that's why it's not falling. If I pulled harder on this, the spring would stretch more and the needle would go up. So what this is actually doing is measuring how much its spring is stretched. And as long as there's no other forces acting, that's a good representation of the weight. How does the postal scale work? Kind of similarly, I'll put a standard mass on. Notice it's registering a little less than, well, around 2¼ pounds. A kilogram is 2.2 pounds. Kind of the same deal. We have the weight of the kilogram, and now there's an upward force balancing it out. So this gets a special name. It's called a normal force. And what's causing it is actually that the electrons in my kilogram can't occupy the same space as the electrons on the scale. They're actually repelling each other. It's an electric force that's preventing that kilogram from falling through the scale. So it's actually chemically really different than the other one, but physically it's kind of similar. The scale's not measuring the weight directly, it's measuring how hard it's having to push back. One force that we're going to use a lot is not very exotic. It's literally a push or a pull. It's just a push. So if it says something's pushing something, you can assume the force is in the direction of the push. So we'll add that on there. There's a lot of ways of pulling, and one of them is using a rope or something like this. We call that a tension force. So we'll add that there. This thing here is called an electroscope, and if you look at it, there's a thin piece of foil which is hooked up to a piece of metal which runs up to this ball on the top. And what it's really good is at showing the force of static electricity. If you've ever scuffed your feet on a carpet in the winter and gotten shocked, you'll understand what's going on here.
basically, when two materials rub on each other, electrons often get taken from one and given to the other. That creates a charge. Since charges repel each other, they must be putting a force on each other. So if we could put a charge on this ball here, we should see a charge go down to the piece of metal and to the post, and they should repel each other. What I'm going to do is I'm going to rub this animal fur on this glass rod. That's just like you scuffing your feet on the carpet. Then you'll see me touch it to the ball, and we should see a repulsion. All right, so I've got it good and charged up. Let's touch it and see what happens. Do you see it? Every time I touch it, it moves farther out. So the force between those two flexible pieces in there, that's an electrical force. We'll be studying that in the spring.
And last but not least, you can have a magnetic force. This is a giant electromagnet. It's hooked up to 120 volt AC wall current. And I'm just going to throw this switch. And clearly it put a force on that ring. So we need to add magnetic. So we'll talk about all these forces over the course of the year. We'll go through the theory of where they come from. We'll see that some of them are actually the same as others, namely push and tension are really just electrostatic forces. But for now, we don't have to worry about any of that. We just need to know that any of these pushes or pulls is going to have an effect on motion, so it won't look like this green line. Its slope will change, its velocity will change. So the one we're going to be studying first is gravity, because it's one of the easiest ones to study. Forces are written in a code that makes you always be able to identify that they are a push or a pull that's going to change motion. So that code is that they all start with F for force. And then you just put a little subscript, a little post-it note on there to remind you what they are. Some of them make sense, others not so much, but they'll help us identify what force it is. Force of gravity is Fg. Force of the spring is Fs. Normal force is Fn. Pushing force, you can just call F, or you could put a little P on it. Tension force is Ft. Electrostatic force is Fe. And my favorite magnetic force is Fb. And when we study magnetism, I'll tell you why. One last thing. Forces cause accelerations. Part of Newton's second law. What causes velocity? Nothing. As you've seen from frames of reference, the old 1960 movie I showed you, the difference between an object in motion and an object at rest is your perspective. So that's why it's sometimes better to say Newton's first law is objects keep doing what they're doing unless you force them. So let's learn about what happens when we force them.